So I want you to look at line 2 here. 255, 0, 255, 0. What is that? Now that you've been through a semester of this class. Is it a sine wave? It's like looking into the tea leaves, right? What do you see? Do you see a sine wave? Square? Is that a time function? It could be an impulse train. Is that? Should I plot that versus time?
It's like an ink blot.
It's an ink blot, right? So I'm asking you a loaded question. So 255, 0, 255, 0. Let's look at all the ways I could plot it. I could plot it versus time with a stem. I could plot it versus time, by connecting the dots. So we could very easily think about this as a time-based function, right? Can I take the Fourier transform of this function? Absolutely. I can either do it by hand, or I can use the myFFT function, provided I knew the sampling frequency, but I could do it, right? Okay. Now, what if I did this? Now what is it? It's a picture. So which is it?
White is 0, black is 255 again.
White is, in this case, white is the first one. White is 255, black is 0. So what is that string of numbers? Is it an image? Is it an audio thing? Is it It's irrelevant. It's just a bunch of numbers. Okay? So that's sort of the point of this exercise. Like, a bunch of numbers is a bunch of numbers. Okay? If you know the context in which those numbers were generated, then you can say something about them. But at the end of the day, once you've sampled whatever it is you're sampling, it's just a bunch of numbers. And you can take the Fourier transform of that bunch of numbers, and it's totally irrelevant whether that bunch of numbers came from an audio, like a recording that you sampled, or if those are color pixels in an image. It's just a bunch of numbers. That's the beauty of the math that you've learned this semester. It's context independent, right? It's just a bunch of numbers. What you choose to do with those numbers or where those numbers came from is separate. But we can take the FFT of those numbers and look at the frequency content of this image. And the reason I'm showing you this is obviously just to kind of prompt you a little bit for the computer assignment you're working on. Okay? The reason you can take a Fourier transform of an image is the reason you can take the Fourier transform of any signal. It's just a bunch of numbers that repeat or don't repeat or whatever have some sort of content. And so it is here. All right? So you would get exactly with the Fourier transform for this signal. Whatever intuition you have that would govern your expectations for the Fourier transform of x will apply for this image. So this image has frequency the same way that anything else does. Yes?
I have a quick question. So your matrix is a 1 by...
Right, 1 by whatever, 8.
8?
I think so.
How come you have y values then?
Oh, it just filled those values in. It's, well, okay. How about, what if I do this? No. What if, it just filled that same color in from top to bottom. Okay, so what if I made another row now? 0, 255, 0, 255, 0, 255. And apparently I managed to screw it up already. Oh, I think I get to do the ... and then the semicolon. No, you need the.
Oh, no.
There. No.
Actually, don't put anything. Just put a colon. Not put the ...
You tell me what to do.
Oh,
No, I'm missing points. That's the problem. 2, 4, 6, 8, 10. I'm missing a pair of points. That's the problem. Thank you. I probably would have figured that out by 11 o'clock. Okay, does that answer your question a little bit better? I added a second row of numbers, so I just get a second row of colors. It's just filling in like this is the first row of numbers and this is the second row of numbers. It's just rendering the image with however many numbers I give it. And it's got to fill that whole space with colors. So if you only give it one row of colors, it's just going to fill in, you know.
So if you make your image, if you make the y-axis large, it's just going to fill up.
Yeah, it'll just fill up whatever the size of the y-axis is.
So it doesn't actually make the matrix a square matrix?
No, it doesn't have to be square. No. Okay, so how does it know that white it goes to 255 and black goes to 0? Because you see what it's doing? I mean, clearly the number 255 is giving you this white square, and the number 0 is giving you this black square. So how does it know to do that?
It's predefined by MATLAB, the color range?
Sort of.
It's the color bar. So if it was in the middle, it would be the middle color.
Right. So what if I do this? I'm going to type color bar. And it's going to give you this neat little bar on the side. And it's going to show me basically when the, and this isn't just MATLAB, this is any like image software, it has what's called a color map. So essentially what it's doing is it knows that it's predetermined that values that are any number with the value of 255 maps to white, and any number any number with a value of 0 maps to black, and anything in between maps to something in between. So for example, if I made some of these like 125, you can see I'd get a gray pixel because 125 is right in the middle.
I didn't know to go to 255. If you just change all your 255s to 126, would still be white and black.
Well, yeah, so you can play tricks on this. So it's all in the color mapping, right? I'm using this function called image scale, which basically automatically looks for the biggest and smallest values in your image and scales according to those. So that's how it knows to take the full range of colors. But you don't have to. You can set the color map to go from 0 to 125. And then anything above 125 will just map to white. Now,
How do you do that?
I'll show you in a second. So let's play some games here. So let's say, so now I'm going to add color map jet. So it turns out MATLAB has a bunch of built-in color maps, right? A color map is literally what the name implies. It's a mapping that maps numbers to colors. Sometimes you might want to have a black and white image. Sometimes you might want to have this kind of image where the lowest numbers go to blue and the highest numbers go to red. But there's other ones, like there's summer, hot. You know, there's different contexts where, like, some of them give better contrast for picking out different kinds of features. Like there's almost like religious wars over which ones make most sense in most contexts. And I don't really care. The point I'm trying to get you to realize is that the mapping of numbers to colors is kind of arbitrary. Okay? And it's just defined by a color map where you can either use a built-in color map or, and here's the cool part, let me see if I can still find the... Okay, so you can actually bring up an editor to edit the color map. So right now, let's see, I'm going to delete this one. Can I do that? Can I delete this guy? I'll just pull him away. Oh, I added one. How do I get rid of those little pieces there? Oh, there we go. So right now it's a black and white. So I can say, and it's telling me that the minimum value is 0 and the maximum value is 255. So the minimum value of 0 is currently mapping to black. But if I want to, there's totally nothing to stop me, except my own stupidity, there we go, from saying that maps to whatever this brown color. Okay, and it's just a different color map. And now I can come in the middle and add another pivot point here, and I want that to be red. Okay, and now that middle point's red, and it just interpolates the values in between. Okay, so the point is, it's arbitrary. There's a bunch of built-in ones, or you can make your own, but it's arbitrary. So, yeah.
So would each one of those columns just be considered like a pixel?
Yeah, each one of those blocks is a pixel.
Alright, so when they say like however many megapixels, is that the entire number of pixels, or is that...
Yeah, that's exactly right. This is a 20-pixel image. Right.
How are images like sampled?
How are images sampled? Well, when you take a picture with a digital camera, that the sampling is happening at the point of when you click the button. I mean, essentially what it's doing is it's got a sensor array, and each sensor array, they're sort of arranged spatially, and each sensor array detects a color, and that's the sample.
Okay, I was just saying, because like on the assignment you said the sampling frequency, because all the values
Right.
are normalized and pi is equal to 1. And I'm just thinking, okay, well, just because 1 is equal to pi, like how can we...
Okay, well, think about it like this. So the best thing to think about for sampling rate is probably dots per inch, if you think about it, right? Because that tells you the number of samples instead of per time per space, so dots per inch.
Will it depend on the camera?
Yeah, or the scan or whatever. But more importantly, more relevantly for your assignment, it doesn't actually matter. So let's say, for example, instead of this x, come back. Instead of this x, let me, and let's put this back onto something a little bit more non-nauseating. So here's a signal x, all right? It's a discrete time signal. It's already been sampled. Okay, what's the discrete time frequency of that what's the discrete time frequency of that x? Right, remember it's always cosine of omega n. So in this case it looks like, right, omega is 2 pi over 10 rads per sample. Okay, and what's going to be the period of this cosine? Remember how to work that? Right, it's 2 pi over that number. So the period is 2 pi over omega, which in this case is 10 samples. So if I were to go, forget the image for a second, if I were to go and say stem m comma x, does it repeat itself every 10 samples? Sure looks that way, right? 10, 10, 10. It's repeating itself every 10 samples. If I now go and look at it as a color, same thing. Is it repeating itself every 10 samples? Sure. Now, do I need to know what the sampling frequency was to understand to have a conversation about the frequency of this signal? No, right? All I need to know is it repeats itself every 10 samples. Therefore, the frequency is 2 pi over 10 radians per sample. I don't care what the dots per inch were. It just has that frequency. So all that's happening, just hold that thought for a second. All that's happening in MATLAB when you're doing the freq z2 and it's showing you that the maximum frequency is 1, it knows, just like you, that the biggest discrete time frequency you can get is what? Pi. Right? After pi, you start aliasing and it repeats itself. So basically, it says, okay, pi is the biggest frequency. We're just going to call that 1. Okay, so if pi is 1, what's this frequency going to be? 2/10. Right? 1/5. So if you were to look at this with freq z2, where would you see your peak? It's a cosine with a frequency of 2 over 10, 1/5. So you would expect to see peaks at plus or minus 1/5.
And then in freq z2, what does the 512 do?
That just sort of talks about how many pixels it actually puts in the 3D rendering of the frequency space.
It slows the computer down too.
It slows the computer down. There's no really, it's all messy. But yeah, basically that's what it's doing. It's basically, if you think about that image that's being generated, it's essentially like the sampling, how densely you're sampling the actual frequency space, like how many points you're actually plotting. Obviously, the more points you plot, the better the image looks, but the harder it is to compute.
So if you wanted to do like another picture that had more pixels, that would slow down the computer even more.
Yeah, absolutely. And I think realistically, like people don't do a lot of like taking Fourier transforms of images, but we're just sort of doing it as an exercise to realize that an image is a signal just like any other signal.
And if you wanted to because you have this sample, would you ever want to have it not sampled, like that, in a continuous domain instead of discrete?
Sure. You ever print out a picture? There you go, right? There's your...
Then you would have to know the sampling frequency.
Exactly right. And when you go to print a picture, that's exactly what happens. Like, you know, they basically, if you're saying, you know, I've got a picture with this many pixels and I want to print it on, that's why they say, like, you can't take a 640 by 480 picture and make a 6-foot poster out of it, right? It's like basically undersampled for that space. So you could do it. It'll just look like crap. Like each pixel will be this big and it'll look awful. But you could do it. But yeah, basically what you say is you say, all right, the picture needs to be at least 300 dots per inch, okay? Or no, rather, a better way of saying it is, if you know how many dots per inch the image corresponds to, then you know how many inches you can realistically expect to print the picture and still get a good-looking picture. So if you had 640 by 480 pixels, 640 by 480 pixels, and you know the image was taken with 150 dots per inch. A dot is a pixel, okay? So then you can say, you can take 640 divided by 150, and that will tell you the number of inches your picture can be, right? So 640 by, so it's about 4 inches by, you know, 3 inches. Okay, but even then it's not going to look all that great. Like typically they say for a nice print, you want to have at least 300 dots per inch. So, you know, you kind of work the math like that. But absolutely, I mean, a picture is just a continuous, that's your continuous time signal. That you're going from digital back to analog. Kind of crazy, right? The real world is in analog. I mean, this is all continuous time, right? When light touches your retina, that's all continuous, real, you know, it's not sampled.
Doesn't your brain sample it though? It samples it at like, yeah, it does. It does it like maybe like 35 megapixels or higher is like the estimated limit of.
I thought that was probably TVs they needed a sampling rate.
I mean, there's a limit to like
unless,
the sensitivity of your brain, but it's not. You're not sampling.
Unless it's just the resolution that.
Yeah, I mean, what you're talking about is resolution, which is like, you can always do these experiments where you talk about like what's the minimum difference between two stimuli that the brain can perceive. Like, yeah, I can show you like 2 points of light, and I can make them get closer and closer and closer, and at some point you can't tell that I'm showing you 2 points of light.
It's more like the accuracy of the continuous time signal, or.
Right, but that's not a sampling necessarily. That's just sort of the. I mean, a sampling sort of implies that your retina is taking an image and breaking it into a grid and then like activating a pixel and then that's it. But that's just not what's happening. Like anyway, it's a long story. Now, okay, let me just sort of give you a a food for thought, and then we'll move off of the images. So, is this a color image or a black and white image? Trick question. It's basically a black and white picture, okay? I've color mapped it onto colors, but it's basically only one layer of color. So if I just give you an image, like if you think about an image as being a matrix, okay? A 2x2 matrix, a two-dimensional matrix. If I just give you one matrix, we consider that to be a black and white image, because you can always map 0 to black and 255 to white, and it's a black and white picture. So the question is, how do you get color pictures? You give, instead of a one layer, you have 3 layers. Okay? You have a red layer, a green layer, and a blue layer. On the red layer, 0 maps to black, and 255 maps to the reddest red. On the green layer, 0 maps to black, and 255 maps to the greenest green, and then ditto for the blue layer. So then what you do is, you take them, you sort of sandwich them, and you add the colors together, and you present them, and then that's your color image. If you add, because red, blue, and green are primary colors, right? If you add the reddest red, the greenest green, and the bluest blue, you have all the colors. You get white. Pretty tasty, huh? Right? And then if you do all the different combinations, you get all the different combinations. Right? You can get purple if you do like a little bit of red and a little bit more blue or whatever it is, like dial the green down and you get purple. And that's how it works. That's why you see RGB. I mean, that's on the web, like you pick colors by RGB. You pick a red, a green, and a blue, and it's basically just summing those 3 layers for you. Yes?
I'm not mistaken, there was a commercial for a while where they were adding a yellow for some odd
Yeah, sharp aquos.
Right.
Specifically, why?
Yeah, well, there's, I mean,
They're trying to increase the gamut of the display.
there's a whole thing to this, and I know about this much of it, and so do you. I mean, nobody knows all, only because nobody knows all of it, right? Basically, the way it works is that there's all these theories about ways that you can improve things like perceived brightness and perceived contrast because of just the way like the receptors in your eye work. So there are people that so they try to play these games where, like, if we add yellow or if we add aqua, like, it'll pop more. I mean, there's no rule that says your building blocks have to be red, green, and blue. Like, you can always have these other building blocks that you can use to maybe improve contrast. I don't really know. I mean, essentially, they're just trying to make the image better by gaming it a little bit. And I think on a TV, like the screen itself is probably, if you have a good TV, is rich enough that you could actually get yourself a better perceived performance. But on a computer monitor, it's all RGB. With printing, it's different. With printing, they use 4 colors, and it's cyan, magenta, yellow, and black, I believe.
Yeah, that's true.
Right, and so like if you see the really fancy printers, like if you want to specify your color, you don't specify it with RGB. You specify it according to the CMYK levels, and it turns out it matters. Like if you express it with CMYK, it'll print closer to the color that you actually think is going to print like. I mean, it just, anytime you're perceiving something, it gets complicated because there's like, we're talking about math, but then now there's this whole other level of how like you look at this and perceive this, right? I mean, there's a yellow layer here, but you might skip over it, right? That has nothing to do with, I mean, it's there, but your brain adds like a layer of processing that people try to, that sort of makes that sort of wash into the, like you can't even tell that maybe there's a dark red in between these medium reds on the side. Okay, that's your brain. The computer's displaying it. So people try to play all these games. They're like, well, clearly a linear mapping between blue and red doesn't work because then you don't have any sensitivity for these things. So you say, well, what if we add, what if we make it nonlinear? What if we try? So anytime you put human perception in the loop, someone's going to try to game the system because it's not very mathematical. Anyway, I thought you might like this. I mean, I always got to, hello. We're back. Anyway, play around with that if you want. I'll post that code. It's kind of cool. And I burned a good 20 minutes. What do you think? Questions?
When you take a Fourier transform at what is it, 1/5?
Mm-hmm.
That would be the only peak because there's only one.
Will it be a perfect peak at 1/5?
I don't think so.
Why not?
Window.
It's windowed. It'll be synced a little bit, right? So, I mean, I could look at the frequency content of this signal in 2 ways. I could just take the FFT of it, right, the my FFT, or if I really wanted to, I could do freq Z2. Let's see what that does for me. Oh, that was freq Z.
But what if you don't have a pattern like, in this case you have a regular pattern.
Mm-hmm.
What if it wasn't a pattern like that?
Well, then you just get, it's just like looking at an audio signal. You'll have some low frequency tones, some high frequency tones. You just get what you get. So there you go. Here's the FFT2.
For our assignment, we were only getting peaks.
Yeah, I was getting
The
peaks.
Y, just like
Yeah.
at the Y doing.
Uh-huh. Now you need to tell me why. I mean, an image is a two-dimensional thing. So think about taking a cross-section. And if you go back to this image that I just showed you, we're talking about frequency because you're thinking about going left to right.
Yeah.
Okay? But there's another way you can go, up and down. So think about your frequency in the up and down dimension.
Constant, so it should be an impact.
It's constant. What's the Fourier transform of a constant? No.
No, sorry. And Bull said, so.
Chew on that. So there you go. I mean, here's your FFT.
But yours is not an impulse.
Yeah, because it's only one layer thick. It's only this. I don't have. It's only one row. Like I don't have a 2D image. I just gave you a row of numbers. I don't have multiple dimensions in my original array. Right. I could do this, though. I could say, hold on, let me try a little experiment here. What if I say x equals rep mat x, let's see, 25 rows, 1 column. Okay, so now what I've done is I've taken my original x, which was just one stripe of numbers, and I've replicated it 25 times. Let's see, is that going to change anything? Ooh, now isn't that interesting? So let's look at it in the x dimension. Do I get my peaks at 2/10? 0.5? Oh yeah, that's nice. Okay, am I getting something that makes sense in the y dimension? What was my what was my signal looking like if you went vertically? It was a constant, right? So you should see what? Is that a constant? Or is that an impulse? It's right, exactly. If you think about that image, it's not exactly a constant in the y dimension. What is it? A constant will go on forever. Does this go on forever? No. How long does it go on for? Just a little bit. So is that a constant?
Not really.
It's a square wave.
It's more like a square wave. And what's the Fourier transform of a square wave?
Kitchen sink.
Who's surprised? Look at that. It's a sinc function in the y dimension. And an impulse in the x dimension. Come on, that's pretty cool, right? Oh, you can't see that. It actually looks even better on my screen. It looks craptacular on this one. Maybe if I dim the lights more. It is now. Did it get darker? Yeah, so now you can see the impulse is a little, you can see it, right? It's sync pulsing. And I'm actually willing to bet, for like double extra brownie points, I'm willing to bet you could even predict the zero crossings of the sync pulse. Right? Because that ain't magic either.
Where you think when the sign equals to 0 in the sync function, you will have to find the Fourier transform of the square wave.
Right, which we've done. I'm not going to do it now. I'm going to leave you. I actually have the other stuff I want to talk about, but you know, I mean, you should think about that. This is, I mean, this is all kind of cool. You should. I would say.
The height will be.
What set the zero crossings of our square pulse before? Wasn't the height? It was the width, right?
But in this case, it's the height.
Oh, right. In this case, it's the height. It's the y dimension, right? What if it's the number of? I wonder if it's associated with the number of pixels in the y dimension. I actually don't know the answer. I mean, that's kind of what's fun about this.
Well, it should be because
There's
like
25 pixels, right? Or 25
well,
columns.
if you relate space
Yeah.
to time, you get you're basically doing spatial sampling. So the amount of space that you take up, which is the amount of pixels, will be like we'll just take. I guess we'll take the reciprocal and you get the frequency.
I will point this out. Yeah, look at this. How many rows do I have? 25. Count the zero crossings. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Plus another 12 is 24. Anybody want to guess that that's not, coincidence? I could test that, right? I did 25 rows. There's 100 columns. There's 100 numbers in each row, and there's actually 26 rows. So what if I change this to 10 now? Should there be more bumps or less? Have a nice day. Anyway, just something for you to think about. So, long story short, an image is just another signal. It's got frequency. You can filter it. You can think of it in the time domain. You can think of it in the frequency domain. You can convolve with it, right? You can do 2D convolution. That's what you're going to do in the. The computer does it for you. You can have high pass filters. You can have low pass filters. right? So part of your assignment is you're going to think a little bit about what it means to have a low-pass filter for an image, what it means to have a high-pass filter in an image. What's a high-frequency event in an image? What's a low-frequency event in an image? Right? I don't want to answer those questions for you. I want you to answer those questions for you.
So you said it's a 2D convolution?
Yeah, there is such a thing as 2D convolution.
Do they depend on each other?
Does what depend on each other?
Like the one dimension depend on the other dimension?
Absolutely. Yeah. They're related. I think once we do 1D convolution in the discrete time domain, 2D convolution in the discrete time domain will make a lot of sense. It's really not that much different.
Is it just a function of two variables then?
Yeah. Yeah. Instead of your impulse response being a number, your impulse or an array, your impulse response is a matrix. So it's like we'll do an example. There's no linear algebra. It just multiplies and adds.
Our zeros are equal to pi over our area. Is it going to be the area of each individual pixel for a square wave?
I think so. I honestly haven't thought about it before I put this picture on the screen. I didn't even anticipate doing this, so I think that's roughly correct. Okay, putting the lights back on, waking y'all up. Okay, I'm going to put the screen up for just a minute. I wanted to show you an example of a digital filter. Because digital filters give you like it's like a whole other toolbox for how to actually solve filtering problems. So all the filters that we've learned in theory are continuous time filters, which basically means that we've learned how to, like if you were building it out of a circuit, that's a continuous time filter. And that's basically everything that we've learned so far. We used a computer to simulate it so that I didn't actually have to send you to the lab and make you wire together circuits and like change all the values like a million times just to learn something. So we've simulated it on a circuit, on MATLAB, but essentially we've been making analog filters. Now we have the ability to do discrete filters. Okay, and we've talked a little bit about how you take the Fourier transform of a signal to get, to look at its frequency content. And I wanted to look at another example. So let's suppose we have a discrete time signal that looks like this. So it's some variable A, and then 1, and then 1. Okay, so there's your h of n. And that's a filter. Okay, that's the impulse response of a discrete time filter. So I'm going to call this the impulse response of a discrete time. Please don't think this is the only discrete time filter. This is just one example of an infinite number of discrete time filters. Okay? I'm just going to use this one because it's pretty straightforward for us to deal with. Now, what did we learn happens when you take the Fourier transform of an impulse response? What do you get?
The Fourier transform of the system.
That's right. The Fourier transform of the impulse response is the transfer function. It tells you whether the system is a low-pass filter or a high-pass filter or whatever flavor filter it is. You with me? So, if we take the Fourier transform of this, we'll get to see what kind of filter this is. Will we not? Let's try that. So, h of omega equals, and I'm just going to write my sum. Okay? So remember, it's x of n e to the minus j omega n summed over all n. So what's my first value of n? Let's start from the left and work our way to the right. Our first value of n is -1, because it's n on the x-axis. So I need x of -1.
Is it supposed to be -1 in the original, right?
No, because these are the y values.
Oh, okay.
Right. So I'm just sort of letting you know that this corresponds to n equals 0, n equals 1, and n equals -1. Okay, so let's start with the n equals -1 term. What is h of -1? 1 e to the minus j omega n. Okay, I can handle that. Plus, now we'll do the n equals 0 term. H of 0 is this parameter a. a e to the minus j omega times n, which is 0. Can you guys see these little squares on the screen? You know what those are?
Pixels.
Plus h of 1, so 1 e to the minus j omega 1. Okay, we good? Now, let me reorganize a little bit. This is e to the j omega. This is e to the minus j omega. And this term is a. Yep. DC offset, that's good. Hey, anybody want to take a guess how I can simplify that? Right, 2 cosine. So all of this comes down to 2 cosine omega plus a. Yes, sir. I can make it start wherever I want. And it turns out, even if it doesn't start at -1, that would just be like introducing a time shift. And has a time shift going to affect my magnitude? No, sir. So it doesn't matter. Okay, so let's plot this real quick. So if I just had 2 cosine omega, I'd have this, right? Where this number is what? Pi. That's 2 and that's minus 2. But now remember, when I'm plotting the Fourier transform, I always want to plot a magnitude and a phase. So if I was to plot the magnitude of h of omega, what would happen to this negative part? Right, it would actually flip. All right, and I don't need to look at the part past pi, right? Because I know it's always going to repeat after that. Pi is always my biggest frequency. So right now I'm just drawing what it looks like with a equals. This is with a equals 0, right? I didn't add a DC offset. So what kind of filter is that? Yeah, it's just going to notch out one frequency. Now, what if I add some non-zero value for a? Like what if I let a equals 1? How? Okay, so let's go back to our original signal. So if my original signal was like this, if I add 1 to it, now it's going to look like that. And then I take the absolute value of it, and it's going to look like that. So now I've got, it's not Chebyshev. It's a simple notch filter that lets you notch out a specific frequency based on your choice of A. See how that works? If I shift this thing up, then my zeroed frequency moves to the right. And if I were to give A a negative value and this whole thing went down, then my zeroed frequency would shift to the left. How can I pick my zeroed frequency? 2 cosine omega plus A. Let's just write that down for a second. Right, so that's my h of omega. So I want you to think about your computer assignment 4 for a second. You guys remember that sawtooth, which had the noise in it? What was my noise like in there? Single frequency. So watch what we're going to do. Instead of trying to get rid of that single frequency with a continuous time filter, like a Chebyshev or something, I'm going to try to get rid of it with this simple discrete time filter. You with? What frequency do I want to get rid of? The frequency I want to get rid of is 5,000. But that's a continuous time frequency. I'm in the discrete time domain now. So what's the discrete time frequency that corresponds to 5,000? Right, do we know the sampling frequency? Does anybody remember it from computer assignment 4? Right, so the frequency that I want to get rid of is 2 pi 5,000 over 44,100. I don't even care what that number is. I'm not even going to type it into my calculator. Okay? Now, I want to make this value, I want to pick a value of A such that my transfer function will equal 0 at that frequency. Right? This is the magnitude of my transfer function. If I want to pick my value of A such that when omega is this number, I get 0. And that way, I'll have a filter that zeroes out exactly the frequency that I want to get rid of. Will I not? So, all I have to do is set that equal to 0, because I want, at this frequency, we'll call that like omega n for noise, okay? At my noise frequency, I want a value of A such that at my noise frequency, the filter response is 0. So this is actually pretty easy, right? I just want A to equal minus 2 cosine whatever that noise frequency is. It's a pretty simple filter, isn't it? Let's try it, and then we'll go home. Okay, so as you can see here, I've already tried this. You can't see squat. All right, so I've loaded the signal. All right, now is this the frequency that I want to get rid of? The one that I've highlighted? Absolutely. Okay, and if I come and type WZ, it'll even tell me what it is. Turns out I don't really care. Okay? Now, I said A has to be minus 2 cosine that value, right? So let's see, what's A? Negative 1.5. Great. Okay, so now I'm going to build myself a filter. Okay, so here's my filter. 1 minus 1.5, 1. All right? And now, all I got to do is filter my signal. So to do that, I'm doing a discrete time filter, not a continuous time filter. So I'm not going to use the LSIM command. The LSIM simulates a continuous time filter. I'm not trying to do that here. I'm just trying to do a discrete time computation. So I'm going to use the filter command. And I'm basically telling it to use filter H. Don't worry about the 1. That's a placeholder for something that we're not going to get into. And X1 is the noisy sawtooth signal. All right? So, we filter it. Okay, you can see I've got an array Y that has the same number of points as the noisy signal. So let's go ahead and plot them. Did I get a T? I did get a T. How about that? Okay, so plot. Oh, I guess we should clear the figure. Plot T, comma X1. That's the noisy sawtooth. And on top of it, I want you to plot T, comma Y, which is the filtered one. And let's make it nice and bold so it's easy to see. Okay, I think we need to zoom in a little bit. Can you see that? Let's zoom in a little more. So what do you think? Did we get rid of our 5,000 hertz signal? Sure did, right? Like a ninja karate chop, right? Just that one frequency got zeroed out. Now, it ain't perfect. If you come and look at the edges, you can see that I've got, it's not quite ideal there. Okay, so right at the edges, it's not really performing exactly how I would. So there was a little perturbation of the high frequency content. And that's actually not surprising, believe it or not. If I were to say, right, this is the transfer function of the system. This is basically that the cosine, 2 cosine omega plus A. Here it is plotted just versus decibels. What you can see is that the low frequencies and the high frequencies are actually not treated the same, right? Just because of the way this filter works. Like it's a cosine that you've shifted and moved up. So some frequencies are going to get passed more than other frequencies. So it looks like here the high frequencies are getting passed more. I mean, you're definitely zeroing out the one frequency that we don't want. But at the same token, we're actually amplifying a little bit some of the high frequencies. And what happens when you amplify some of the high frequencies that you weren't too crazy about? You get little high frequency wiggles that you didn't want, right? And that's exactly what you see, right? We have these little high frequency wiggles right at the edges. You use a less crappy filter. I mean, you get what you pay for, right? I mean, that's about as low weight of a filter as you could want, right? I mean, just 3 points, three taps on your filter. That's super duper low overhead, right? Very easy to build. It doesn't require a lot of stuff. But it's not a great filter. So instead of 1A1, you try with 5 samples or 10 samples. I mean, there's a whole. We just barely scratched the surface with designing continuous time filters. There's a whole theory about how to design discrete time filters. There's finite impulse response, infinite impulse response. It goes on and on and on. All right, but the point is that you just design a less crappy filter. With this filter, it's about as good as you're going to get. But still, I think you're hard pressed to say that that's not pretty good. That's not pretty good performance. So just one last parting thought. Let's just look at the frequency content real quick. So now you're looking at the Fourier transforms of the input and the output. The original signal is the blue one. The filtered signal is the red one. Okay, so what do you notice? First of all, the 5,000 hertz peak is gone, right? It doesn't, it's there in the blue signal, the original, but it's filtered out in the red one. Okay, then the next thing you notice, right, there's all those high frequency harmonics were actually amplified, okay, which is what we expected from our crappy filter, and that's why we saw that little wiggle. And some of the low frequency harmonics were actually divided down a little bit, okay, which is, it is what it is. But still, again, for 3 samples, it ain't bad. Right, for a 3-tap filter, it's pretty good. Okay.
Are most filters implemented digitally nowadays?
It depends.
Or do they each have their own kind of application?
They each have their own kind of application. I mean, generally speaking, you have more flexibility with a digital filter, but you can't really apply a digital filter unless you have a signal that's been digitized, right? So sometimes in order to even clean your signal up enough that you can pass it to an A to D converter, you might have to do a whole thing of amplifying and filtering in order to even clean it up enough that you could pass it into an analog to digital converter. So it's not really best to think about it in terms of one or the other, right? Each one has a role that it plays. And so, you use the right tool to solve the right problem. But yeah, generally speaking, you have a lot more flexibility in the digital domain. So if you can digitize your signal, yeah, digitize it and then just, deal with it on a computer. If you decide to change your parameters, you don't have to rebuild your circuit, right? You just change your code a little bit and it's fixed. But it's, like I said, sometimes you can't even sample your signal until you've done a whole bunch of filtering and whatnot, and that's got to happen in the continuous time, in the analog domain. And then you're stuck. You just have to do it. Okay. Sorry, go ahead. Yeah.
And then you design whatever. That's also.
That's giving you a digital. That's giving you a digital filter. Again, there's a whole theory on how to do this, and a lot of times, what happens with the digital filters when you design them is it essentially starts by designing an analog filter, and then tries to pick filter taps. Like it basically tries to make a digital filter that captures most of the essence of that continuous time filter. That's one way of doing it. There are other ways, but so they're related, and you sort of have to understand how they work. But they're different. They have different properties and do different stuff.